Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
All right, let's take a look at our homework for lesson 7.1.5. Our M&Ms that we're covering now are covering officially the box plots. We've talked about box plots a fair amount when we've been introducing some of the other data statistic concepts and data displays. The box plot, which at one time we called a box and whisker plot, box plot's easier to say, is a kind of data display where you can see the spread of the data, and it breaks up the data into 25% intervals. And so here is your typical data. You've got to find the minimum, you got to find the maximum, and you find your median. And this is the same data that we had from the previous week. What was it, 7.1.2 maybe, when we were learning about or writing down in our journals about the quartiles and the interquartile range. So finish this process. I told you that the box plot that I sort of showed you wasn't really accurate because it wasn't referencing a number line. So let me go ahead and do this now. We're going to take our minimum, which we know is the number 2, right? It's this number right there. We've got our median, which was the number that's in the middle. That was the 14. And it's in the middle after we've put them in order from least to greatest. You can't find the median if you don't have this ordered. The maximum is 43. And if I'm not mistaken, the first quartile was the number 8 because that was the number between 7 and 9. This is the lower half of the data, and the median is the number in the middle. Since you got 2 numbers in there, you find the average of those 2, and so that's 8. So that's going to be the first quartile. And then the third quartile was halfway between the 32 and the 36, which is 34. So now that we've got these 5 pieces of data, we create a properly scaled number line. We find out where would the 2 be on that number line. It would be right around here. Where would the 8 be? It would be right around here. Where would the 14 be? It would be right around here. Where would the 34 be? It would be right around here. And where would the 43 be? It would be actually, I think 43 is probably here, not there. That looks more like 44. And we would just go directly above this, and we would mark these spots, and that technically is supposed to be here. And that becomes our interquartile range, boxes in the median in the 2 quartiles, and then your whiskers go to the minimum and to the maximum. So that's how we do a box plot. And remember, the whole idea of the box plot is everything in here, or everything in each one of these 4 sections, is 25% of the data. So we don't have any individual data here if we're not able to see any of this. If you are able to see it, wonderful, it's there. But now we can say, all right, 50% of the data is 14 or greater, and 50% is less than 14. 75% of the data appears to be greater than 34. No, 75% of the data is less than 34, and 25% of the data is greater than 34, and so on and so forth. So just one other way that you can look at data to see the spread of the data and how it's evenly distributed 4 ways into quartiles. So let's put this into practice. Erica is tracking the depth of water in her local creek. Her first 9 measurements are below in inches. 16, 15, 13, 12, 17, 14, 11, 9, 11, 9, 10, 9. This is raw data. It's not in order. In order for us to find the information we need to find for our box plot, we need to put it into order. So we go through, and there's 3 9s, there's a 10, there's 2 11s, there's 12, there's a 13, there's a 14, there's a 15, there's a 16, and there's a 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Make sure I've got 12 in my ordered data. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I count them just because the most common mistake people make is they don't put them all, they don't get all the numbers accounted for. And so they work through the processes, right? But if you missed one number, everything else gets thrown off. Excuse me. So let's start with the minimum and the maximum. There's your minimum, there's your maximum. Okay. And let's find our median. There were 12 numbers, so we're going to find 2 of them in the middle, are these 2 numbers right there. So the halfway point would be 11.5, so there's your median. And then when we need to find the lower quartile, we're going to take everything below, and there's 1, 2, 3, 4, 5, 6. So you're going to have 9.5 is going to be your first quartile, and 1, 2, 3, 4, 5, 6, the halfway point there is 14.5. So that's going to be your upper quartile. So let's find your minimum is 9. Your lower quartile is going to be at about 9.5. Your median is at 11.5. Your upper quartile is at 14.5, and your maximum was at 17. So we're going to find each one of these points below a line, box in the interquartile range, and you've got your box plot. When you finish your box plot, you should always label each one of these numbers as a part of your box plot. That completes the process. You must reference a number line or else it will not work. You're not going to get everything proportionally scaled out and spread out to see the true spread of the data. And remember, one of the things that I showed you in the M&Ms from a previous lesson was that you can sometimes identify if there's an outlier, if like your maximum is way out here and the rest of the data, the 75% is clustered together, but you got something way far out here or something way far down there. That's an indicator that you've got an outlier, and you want to account for those outliers when you are drawing your conclusions about your data. All right, if 1/4 of x is 15, did I say 15? Is 16. What is 3/4 of x? Justify your answer in more than one way. Okay, so we've got a few different processes here. 1/4 of x, this would be 1/4 right here, is 16. So 2/4 must be 32. 3/4 would have to be 48, right? Because 3 times 16 gives you 48 for an answer. So using the diagram, we were able to determine that 3/4 of x is 48. If we set this up as a proportion, 1/4 is equivalent to 16, so 3/4 would be equivalent to some number there. If I triple this number here, then I would have to triple 16 and we would get 48. That's one way of doing it. Or I could have used proportional reasoning and done cross multiplication. And so you get 3/4 times 16, which is 12, will be equal to 1/4 times y, which is 1/4 y. And then when we multiply each side times 4 to cancel this guy out, you get 4 times 12 is 48. I'm not quite sure what I was doing here. Oh, well, 3/4 of x is 48. And I don't know. I don't think they ever asked us what x is equal to. But do we have more in there? I'm confusing myself. I can't remember exactly why we did that. But what does it say? In more than one way, I did it this way. I did it this way 2 times. And every time we got 48 for our answer. So we're good. All right, Luann talked on her cell phone for 180 minutes using 3/7 of her total monthly minutes. So 3/7 right here. That represents 3/7, right? 1/7, 2/7, 3/7, and this was a total of 180. So you break that up into 3 equal parts. That means that 1/7 must be 60. And then if you multiply 60 times 7, you get your total of 420. Okay? So 3/7 of x is equal to 180. If you multiply each side times 7, that gives you 3x's is equal to 1,260. And you divide by 3, you get 420 as well. So a few different approaches that you can take here to get to your answer. I used the diagram and I used an equation. Actually, I want to check something out here. I almost did this the other day. Remember how our percent proportion says part over the total is equal to percent out of 100, and this ends up being a fraction, right? So what if I decided to take our part, which was 180, our total we don't know, but the 3/7 there. I'm curious, when we cross multiply, we get 3x is equal to, all right, calculator, I think I did it over here already, I did 1260. Yeah, that ends up giving us the exact same thing. So when we have, instead of expressing this as a percent, when it's expressed as a fraction, we can replace our percent over 100 with the actual fraction and still solve the problem, and we get the correct answer. Woohoo! A new strategy to use. All right, write the inequality represented by each graph. So our boundary number is 3 here. 3 is circled, but it is not shaded in, which means x is anything less than 3 because all the numbers less than 3 are being shaded in. Our boundary number here is -1. It's circled, which means it can't be equal to that, but everything less than the -1 is a solution, so x is less than -1. Here, our boundary number is the -2, and it is shaded in, which means that it is a part of the solution set. So everything greater than -2, as well as the -2, is a solution. So x is greater than or equal to -2. Tires R Us is having a 30% off sale. And the savings, right? The savings means how much is the discount on a tire that regularly costs $45. So if they wanted the sale price, they would have asked for the sale price. So I'm going to choose to use the 30% as our multiplier. So 30% of $45 is 0.3 or 0.30, right? 30 hundredths, but we'll just call it 3/10 times 45 ends up being $13.50. So that is the correct answer. That is the amount of the savings. But if you want to figure out the sale price, you take $45 and subtract away 45 minus $13.50. That is the sale price. Now, let's verify. I know I've already proven it to you, but I'm just going to do it again. If I choose to multiply this times 0.7, that's going to take me directly to the sale price. So 7 times 5 is 35, carry the 3, 28, 29, 30, 31. And there's one decimal, so we're going to put that back in. Let's add a 0 for the number of pennies, and we get that for our answer. So once again, you got 2 multipliers that can be used in this situation. If you want to find the amount of the discount or the amount of the savings, use this as your multiplier. If you want to find the new price or the sale price after the discount, use this as your multiplier. All right, and holy free holies, this does not look like a lot of fun. These are expressions, and we need to simplify them or write them another way. So in this case, you're just going to send in the dive bombers. 3.3 times x, and 3.3 times 4 ends up being 13.2. So that's your final answer. Here, we're going to have to send in the dive bomber, and this is where students are going to make a mistake. So I'm going to work this one out entirely. 9 minus 5.5x minus 3 times -2x plus 1. That minus sign is a part of the 3. If I change this to plus -3, you would have to send in -3 times -2x and -3 times 1. The most common mistake that people make is this. They'll say -3 times -2 is positive 6x, but then they'll say 3 times 1 is 3, and they'll make that positive 3. But it has to be a -3 because that's a -3 times a positive 1. So if you got a different answer, I bet you anything it's right here where you wrote that as plus 3 instead of -3. Now let's look and see if we can combine like terms. You got positive 9 and a -3 is going to give you positive 6. And if we take, let me do this in blue, -5.5 plus 6, you got more positives than negatives, but only half of a positive more. So if you take 6 minus 5.5, you get 1/2. So this ends up being 1/2 x plus 6. And this problem should be fairly straightforward. Distributive property, then combine like terms. If anyone needs me to work that out, let me know. And that is it for our homework. How much time did we use? Not too bad. All right, moving on. Take care. Bye.
Hey, feeling good, like I should. When in dark, walk